Today, we are discussing our PhysicsQuest kits. So for those of you who might not be familiar, PhysicsQuest is one of the programs we run here at APS Public Engagement. And these are public engagement activities that are created for middle school audiences that are rooted in current physics research. So every year, we come up with different activities under a different physics topic. We've done, waves, we've done both motion and sound, we've done, plasma, we're going to do quantum, we've done a variety of different topics, and these are all kind of ways for middle school students to be introduced to, fun and relevant science in a more kind of hands-on way, as they're kind of learning more about the physical world. Physics is, not something that's typically taught to the middle school audience. So our PhysicsQuest kids kind of give them a little brief introduction to it in a little bit more of a fun way than, the typical physics learning model, which is, math, very, very math heavy. So we like to do a little bit more interactive, accessible activities. And just to give a brief little shout out, the image that you see on your screen, that is Nicole Schrody. She is our program manager for PhysicsQuest. She unfortunately has the flu, so she wasn't able to join us today. But I want to give credit where credit is due. PhysicsQuest is her baby, but we can also answer any questions that you have about PhysicsQuest. A little bit more kind of on what the evolution of PhysicsQuest has looked like. So we began in 2005, and we have a backlog on our website of all of the past lessons that we've done. But in 2023, we went through and we updated all of them, so that way they are more readily available online. You can find them all, like I said, on our website that was dropped in the chat. And our update also included evidence-based pedagogical strategies and implementation tips for the teachers. So for example, when you open up the lesson plans, for like each theme has its own web page, and then it's broken down by the 4 activity types. You'll click on whichever activity you're interested in, and then it will pull up all the information you'll need. So it will have, the materials that the teacher would need. It will have, step by step what to follow. It will also have, the teacher tips that are super helpful. So this might include terms that are unfamiliar that you might want to be, explained to, because sometimes the teachers aren't super familiar with these topics either. Kind of tips and tricks on what's a good way to implement this kind of portion of the activity versus this part, and just kind of giving them a little bit more guidance. And under our new model that we've just recently started, we have been really kind of trying to collaborate and co-create with, subject matter experts. So for each of the 4 activities that we develop, we have been partnering with different APS units to create these activities, along with getting teacher input on how it's going and how accessible it really is. So we've partnered with, for example, last year for the 2024 to 2025 school year, our PhysicsQuest kit was all about plasma. So we partnered with the Division of Plasma Physics, which is DPP, for creating 4 different activities. Again, these are all based on current research that's happening. So this really kind of allows members a way to look at their research and explain it, and kind of based in an activity instead of just like a straight explanation, for a middle school audience, which is not super typical when you're explaining, higher level research. And like I was saying, yeah, this is just a really great way to promote topics that are not traditionally taught in the middle school. So plasma, which was our last year, and then our next year, 2025 to 2026 kits are going to be on quantum to celebrate the International Year of Quantum Science and Technology. So it's another kind of topic that's not typically taught in middle school. Although these are focused for middle school audiences, our PhysicsQuest kits can also be used in high school. You just might need to age up some of the activities a little bit, but it's very easy for teachers to adapt them. In our last year's cycle, when we were giving out our free kits, which we have a number of each year, we had about 50-50 distribution of giving them to middle school versus high school. So you can see kind of like the breakdown there. A little bit more about what the evolution has kind of looked like. So with each of our kits, we have put together this kind of, not mascot, but more like imagery that is represented by it. So in 2005 to 2009, we had these kind of model where it was more kind of, the famous physicists. So like, who is it that comes to mind when you think, physicists? So Ben Franklin, Albert Einstein, Marie Curie, those are people who, are very obviously physicists to young students. And then in 2010 to 2018, we shifted to include these Spectra comics with our PhysicsQuest kits. So these were just short comic books for students, and it was all about Spectra, who was our superhero, who was using physics topics to, fight the bad guys and save the day. And then in 2019, we shifted to our current model, which are narratives that we include with our kits and our lesson plans. So this kind of introduces students to, what does a modern physicist look like? Who might be your next door neighbor who's a physicist that's not, the Albert Einstein model, as well as, the breadth of careers that there are out there for a physicist instead of just the stereotypical lab model. But this really kind of shows students, what the day-to-day of a physicist looks like. We've also had like interviews with a lot of these physicists, so you kind of get to learn a little bit more about what their journey has looked like and maybe kind of what struggles they've overcome, which we've learned that students really respond well to. So this is another really cool aspect that we have as part of our PhysicsQuest kits. But without further ado, I will stop talking and I will turn it over to some of our developers that we have worked with for our 2025 to 2026 Quantum PhysicsQuest kits. So we have 3 different groups presenting today, and I am just going to introduce them all at once, and they will take it over from here. So up first, we have Malcolm Johnson and Zach Simmons, who are joining us from the Milwaukee School of Engineering. After them, we're going to hear from Reggie Wilcox of the Massachusetts Institute of Technology, along with Fong Deng and Joseph Henning of Louisiana State University. And then last but not least, we're going to hear from Kimberly Becker of Centaurus High School, as well as Danyel Cavazos of University of Chicago.
All right, so hello everyone. I am Malcolm Johnson, and alongside my colleague and professor, Dr. Zach Simmons, we are going to be talking about more so our journey into how we got into quantum, how we sort of collided fields, and how it sort of branched out into what we do at school and what we did for this physics kit. So just starting out, again, my name is Malcolm. I am a graduate of MSOE, where I got my bachelor's in software engineering and am currently a machine learning master's student, doing that part-time while I have a full-time job. And then my colleague, Dr. Simmons.
Hi, I'm a physics faculty at MSOE. So yeah, we're a pretty small institution. We are technical institution, so mostly engineering degrees and computer science and those sorts of fields. We're definitely we're not really big enough to support science degrees in and of themselves. So as a physics person and somebody who's really interested in that area, I'm always looking for ways to kind of introduce more and more interesting physics to students, our engineering, primarily engineering and computer science students. And one of the things that I'm trying to get across in our talk is just that I think quantum computing in particular is kind of ripe for being a vehicle to talk to students about some of the most interesting ideas in physics that for students that otherwise wouldn't necessarily get exposed to those ideas. So a lot of engineers all take physics, but they take mechanics and they take intro E&M, and they're taking kind of the basics, and they don't get to see some of the fun stuff. So I think quantum computing can be kind of a way to sneak it into things that they see, and that's kind of what I have been thinking about a lot with this. So
how it started on my end was kind of along the lines of like one of those crazy plans where you have just a bunch of scraps, like I need to build a rocket, I have a rubber band and a few sheets of paper. So how I sort of started was I downloaded an informational app called Just Quantum. I talked about all the sort of physics sides of things just in like bite-sized pieces. And I would read that on occasion while in like my freshman year. And then I stumbled on 2 YouTube videos that more so taught me that this is not a matter of can I or can't I. It's more so that I'm going to try, and it's going to be interesting in some degree, since I'm interested or I'm curious about these quantum topics. So the videos by Anastasia Marchenkova and the Wired video that features Dr. Gershon from IBM talking about quantum computing at 5 different levels. And what really got to me was her use of a coin to just represent qubits, and in order to be able to calculate data or hold data and compute things with said data. And then Marchenkova's video more so just told me like where to look and how to go about getting started with a more structured sort of course. So I took one course that she recommended from EDX, and that's how I gained a more competent understanding of the basics when it came to quantum computing. So the problem that we've faced at school was just more so branching or making more people or more kids, more students aware of this fascinating and ethereal, in a way, sort of field. And that came through when we started taking a look at what is our current lineup, or what's our current understanding. Students at school, some of them know what quantum computing is, but it's this sort of mysterious thing. There's a lot of hype around it, or at least around the word quantum. The topics of themselves branch out in 3 areas that can be challenging for students. But how we saw it was that engineers were going to be a massive part of how this field continues to progress. And I think we see that now with how software or hardware engineers can get into quantum by just looking for those opportunities and being open to working with these new types of computers. So with that in mind, and the understanding that our general audience was engineers, or more so just tech-related engineers, that's how we sort of started out.
I was just going to say that a lot of the things that we've been thinking about with our audience of students on campus are totally relevant for this audience too, like folks that are interested. But there's so much quantum this and quantum that's kind of in the background of pop culture and society. So it's nice to want to give folks a little more concrete and correct. If we can contribute to that in a little way, I think that's cool.
So the topics we sort of divided amongst ourselves was, how do we filter this field into bite-sized pieces that our student base can understand. And it was more so just branching out into the important topics that we wanted kids to get a grasp of. From the math side, there's going to be a lot of linear algebra and probability involved. These are classes that any of the engineering majors take, and offered some familiarity when we're exploring those topics. But when it comes to like either freshmen or sophomores, they have yet to dive into those classes. But we still try to make it approachable to them, just by going through all the linear algebra that they need for this type of computing. And then for the computer science side, I can talk largely about this because I've had to explore all these different whys and hows that quantum computing can answer, so that we can present that to the students. And these topics come in the range of like error correction, hardware, how does the software, or how do we get started with the software? Where does the hardware meet the software? These kinds of topics that more so that got talked about in old computer history, but are peeking their heads again in this time, just because history has a way of rhyming, not necessarily repeating. And then from the physics side, Dr. Simmons, do you have anything to add to that?
just that kind of like I mentioned before, it's cool to have an application to expose, like at least at our institution, and I think in a lot of curricula, people that are studying technical things, even like engineering and computer science, don't necessarily get to talk about some of the cutting edge things that are happening in those disciplines. If they're just, they just want to be whatever kind of, at that level. So I like that we have the opportunity to kind of introduce some of these topics using quantum computing as a vehicle for that. So I think the stuff on the next slide too is, yeah, so this is kind of my message. I kind of said this before, but just that, some of the things that are kind of some of the largest objects of fascination and interest in physics, like entanglement, are so central to how quantum computing works that it's nice to be able to use that to expose students to that. And I think, this kind of makes me think of something that I don't like about physics is it can have this real arrogant and kind of intimidating thing. And I think some students are intimidated by it. And I don't like that. And I love that this gives a topic that we can kind of get into some of the fun stuff and kind of hopefully short circuit and get around away from, you have to study tons and tons of physics before you could talk about something like quantum computing, because that's how the route that it is for a lot of students, I think, in exposure to some of these topics.
So how it progressed for the past few years when I was dealing with these topics at school was, alongside my schoolwork, I would spend a few nights just going through the linear algebra, establishing that I understand what all these operations are doing or what they sort of express about the quantum gate side of things. And then I would also do a few presentations on what I found, so that I could present it to the software engineers, the computer science people, computer engineers, these different types of audiences that should be made aware. In the times that I did these, albeit they were pretty content dense, and it still can be quite a challenge to get through within like a 30-minute or even an hour presentation of like, what should kids need to learn at the start? And where could I improve in talking about these concepts? And then alongside that, we decided to develop a book club based off of Thomas Wong's book for an introduction to quantum computing. That helped us establish like people in this book club should read X or Y chapters, and we can talk about the concepts that lie within during a weekly meeting. So that's what we did it was 2 years, I believe, or 3, something like that. But yeah, that was a good time, and we learned a lot just by sort of trial by firing our sort of understanding of how does physics collide with mathematics, that outlines what we do with the computer science.
I got a huge kick out of that. I would just mention that I'm not an expert in that area. That wasn't my area of study, quantum computing. So reading some of these books with the students was a lot of fun. I definitely learned a lot from that. And then, yeah, another outlet for us was this, the PhysicsQuest opportunity. So why we're here today. So we, one of them, I mentioned entanglement. Entanglement is so central to quantum computing. And it's also this, topic that's, it's in movies, it's depicted all over the place. And so we thought that this was a really good topic to try and use for the PhysicsQuest activity. And so we came up with a game to try and teach kids basically qualitatively about the consequences of entanglement, and less about looking at the math of how this works and more about what the kind of conditional probability of it would look like. And so that was our goal with the activity.
Yeah,
And
so the point of our activity was we have 2 players pitted against each other, and they both had a set of coins and a set of targets. On the right is an example of what we outlined as a simple target, just with the nucleus as the dead center. Kids would spin their coins to try to reach the center or hit the center, and then when one of them did, they would slap it down. And then the other would either hold theirs in place by clapping it, or also slam it down depending on the state of the game. We had 3 different states, entangled, 2 different states, same and opposites, or just standard play. For 2 standard qubits ran through H gates or through 50/50s. And then the kids would grab points by who hit it in the center first, and was their prediction correct? AKA, did they get heads or tails, and did they predict whether they got heads or tails for a certain match? So we had 3 matches to a game, and most points wins a match, and then best 2 out of 3 there. So developing that game was a fun journey in the sense that it's immersive enough that we believe, and there's a lot of interaction that goes on when we talk about playing in different states. How many rounds do we add to a match? And those different features that help with kids' understanding of like why does, or when we have entangled states, why do the heads or tail, or why do the certain points get correlated together, or point pairs, more or less.
Yeah,
But that was
tough.
our sort of journey there.
I was gonna say it's tough to explain a game without showing you playing a game. So it's kind of like winning the game is really winning in that hopefully they learn a little bit about the difference between entanglement and things that aren't entangled. Just because it's depicted so much, that we thought that it would be a good idea to show students a little bit more correctly what that means. And so hopefully the game accomplishes that. I guess we'll see. We'll get some feedback from teachers and see how it's working.
So yeah, where we are next is currently we have a quantum computing class that we'll talk about.
So yeah, I kudos to Malcolm for definitely prodding me along and showing me that there's a lot of interest in this topic on campus. So this year, actually in an hour and a half, I'll have class. We're trying a quantum computing elective class, and it's been a way to go into more depth than we could in like a book club, and expose some of our students to more of these ideas. And it's been a lot of fun for me, definitely this term working on that, and we hope to have it be a feature of things going forward. So
yeah, and then on my
class
end,
at the university. Yeah.
Yeah.
What are you up to, Malcolm?
And then on my end, Dr. Javier Mancillo, I believe is the last name, but he just released a book that I'm definitely interested in when it comes to what I currently study as a master's degree, and then incorporating quantum into that. Just looking to read his new book, bought it off of Amazon, and then I've been trying to work through a paper that goes through like an implementation of Shor's algorithm, just so that I have a better understanding of the low-level details or lower-level details of what goes on in said algorithm. Because whenever we've taught it at university, it's always been at the high-ish level, such that we're just talking about how does the math work? How do modular operations function such that this algorithm can succeed at its purpose? And that part's or going through that paper and re-going through that paper and re-going through that paper has been quite fascinating, quite frustrating at points, but it's been challenging but good work.
Oh, and then we stuck an International Year of Quantum on there as well. So another next step for us is definitely taking advantage of stuff that's happening this year in this area. It's cool how many different things are happening all over the world.
But yeah, that concludes our presentation.
All right, so I'm here today with I'm Reggie Wilcox, along with is my bottom of my screen showing up for you guys? No, it's fine. Okay, so I'm Reggie Wilcox. I'm here today with Joseph Henning and Fong Deng from Louisiana State University. And we're going to be talking to you about developing our PhysicsQuest activity, which was Photon Frenzy. So At the very beginning, when we give the activity out to the students, we have this introductory video that we played, that we made for them. This was done by the group out at LSU. And the idea behind this video was to try to orient the students and get them thinking about light as quantized particles, thinking of it as photons and how those can interact with matter, specifically with electrons, and how we can learn properties about light through that interaction. So that the main goal of this activity for us was to demonstrate the quantization of light into photons using a engaging and cost-effective school activity. We specifically settled on the photoelectric effect in order to demonstrate that. And for those of you not familiar, the photoelectric effect is a photocurrent that's ejected from a metal when it's illuminated with light. And there are several different properties of this photocurrent that's ejected as you change the frequency and intensity of the light. And you really need quantum mechanics to explain all of these properties of the photoelectric effect. For this activity, we specifically narrow on this plot C here, where if you shine light with too low of an energy or too low of a frequency, you're unable to eject any photon or any electrons from it. And when you exceed that cutoff frequency, you get a constant electron current in terms of light frequency. And so that's due to the electron binding energy to the metal. You need the photon to exceed that energy. So for this activity, instead of shining light on metal, we used an LED to demonstrate this concept, where the LED band gap shows a similar thresholding behavior to the electron binding energy in a metal. The basic design of the system was we use a LED as a light sensor, and then drive an amplifier with this, use that to drive an amplifier, and then that can turn on an indicator light. We use a blue LED for the sensor so that it would be sensitive to blue light or any light with higher energy, and then insensitive to lower energy light. So when we shine a blue light on the light sensor, the indicator light will turn on. However, if we shine a yellow light on it, the light won't turn on anymore. And so this thresholding behavior shows a similar effect to the photoelectric effect that we expect. And so next, this is just a little part of the demo video that was sent to teachers to show this effect in action. Find that blue light can still turn on the LED. While yellow light is incapable of doing so. So that is kind of the way that the device functions. You could see the little printed circuit board was the device that the students were handed, and they had these flashlights and gel filters to explore illuminating it with different colors. This here is a schematic of how the device works. It's just got a sensor LED that was on the board that drives a Darlington pair of transistor amplifiers. And that's used to turn on a indicator LED when you shine a sufficiently or the right color of light onto it. The activity flow for the students was they would watch this intro video that I showed you at the beginning that was made by LSU. Then they assemble their own devices, which is just hooking up the LED and putting the battery in. And then they test their board using white light to make sure that it works at all. We then asked them to look at the blue and yellow light separately and not shine it on the board, and form a hypothesis of what's going to happen when they put blue versus yellow light on the board. This was made to be a little bit misleading for the students, because looking at the light that passes through the filters, the yellow light does look brighter to the eye than the blue. So we were, hoping to trick them a little bit so that they would get the wrong idea of what was going to happen, and then they'd be a little more motivated to figure out exactly what is going on. And so after they form their hypothesis, we get them to test it, and then they'll formulate their conclusions by working through a guided worksheet of questions that we give them. And then at the very end, there's a concluding video, which I'm not going to show you, but was also made by LSU, that nicely sums up all of the quantum properties that we were seeing and helps to make sure that the students really understand what was going on with their experiment and kind of put the pieces together with the quantum mechanics and the real world and what they were seeing. So next, we're going to go over the high-level development process and how that collaboration worked with LSU and other universities. So it kind of started off, wanting to demonstrate quantum properties of light to these middle school students. And there were kind of three different areas that the activities we looked at went in. There was quantum entanglement of light, quantum measurements, and then quantization of light itself. The quantum entanglement and quantum measurement went into we're using a polarization filter demonstration activity that was put together by Bard College. These same properties of an entanglement and measurement went into a variation of the two-slit experiment that LSU was developing, and I specifically looked at the quantization of light into the using the photoelectric effect with LEDs. So for the collaboration process with us, we in July 2024 we initially met and compared all our ideas, which were three different ideas were approved by the PhysicsQuest board, and so we had these three ideas to work with and figure out what made the most sense going forward. So we decided to independently develop each of the ideas at our respective schools, and did that for a couple of months, and then met back in September to evaluate the feasibility of each of our designs. It turned out the two-slit demo required more precision than was expected from a middle school student in order to set it up and see the effect. And the polarization filter fabrication was too expensive at the scales required for PhysicsQuest. So we settled on the LED photoelectric effect, and then kind of went into two separate development paths. I worked on refinement of the device itself, getting that into a version that was acceptable for production, as well as writing a lesson plan on how the students actually want to use this board in the end. And then the students at LSU worked at developing a activity video for both the introduction and conclusion to it. And then later, as the lesson plan was being finalized, we kind of had a feedback there where we made sure that the ideas and the concepts that were touched on in the lesson plan were reflected accurately in the video. And then finally, we wrapped everything up and had a final product delivered in December. So for the collaboration process, there were a couple of pros and cons to it. One of the big pros to it is I think it allowed a riskier development process because we had several independent ideas that were being worked on in tandem. So the likelihood that we don't end up with a viable product in the end was much reduced. So we could explore riskier ideas and perhaps more ambitious projects. It also provided a more comprehensive activity in the end because the collaboration allowed the development of the video for us. If I were a single institution working on this, we would not have had the video to accompany it. And I think that having those videos does add a lot to the activity for the students. There was also, a more first group of people applying input to the lesson plan, which I think made it more comprehensive and stands up to scrutiny better. And then, it was great to meet new people and make new connections. On the con side, the development process was a bit longer. I think it probably added about 2 months to the development process compared to working on it solo. And kind of related to that is, coordination across institutions can be a little tricky, especially trying to, get a meeting that lines up on everybody's calendar. And then the last part is not necessarily a con, but something that you need to think about when developing these activities is you need to have a good division of work. So for like a smaller project, it can be hard to split it up so that multiple people can work on it. But that having the device development and the video development worked very well for us as a division of labor for that. And so this last bit, I'm just going to be talking to you about the specific development of this LED photoelectric device. So the initial concept for me was to demonstrate the photoelectric effect in a cost-effective classroom experiment. But in order to actually arrive at the final design, I iterated through 3 different ideas before I finally settled on something that actually worked and demonstrated the idea that I wanted. The first idea I had was using a photovoltaic cell to directly drive an LED so that you could shine a light on the photovoltaic cell and the LED would turn on. And then I thought you could change the color of applied light to the photovoltaic cell and then it might no longer turn on, which had I thought was a pretty cool idea that you don't need a battery to turn on this LED, and it was a simple design that the students could put together themselves. The biggest drawback for that, and it was a fatal flaw, is that photovoltaic cells are designed to operate for a broad range of wavelengths. So it's hard to find a photovoltaic cell that's not going to turn on at is going to have like a null in the response at any frequency that you want. So I was not able to find any commercially available cells that would work for this. So this never made it past the prototyping phase, or sorry, the research phase, and it was never prototyped. The next idea I had was having putting a photoresistor in the circuit with a battery and an LED, so that when the photoresistor, if the dark resistance of the photoresistor is high enough, the LED wouldn't turn on, and then if you illuminate the photoresistor, it would lower the resistance and the LED would eventually turn on. And then you could vary the colors applied to the photoresistor and maybe see some kind of cool effect that way. This required a battery, which was a little bit of a downside compared to the photovoltaic cell. But the main problem with this was the contrast of the photoresistor was too low, so that I was not able to get it to turn on and off using just this simple circuit. And it would need some active thresholding circuit, which would require a PCB and advanced electronics to do that. And also the sharp cutoff we see in here occurs at low wavelengths, which would kind of be contrary to the photoelectric effect, where you're seeing the low wavelength light no longer turns on the LED. So that was also a drawback. I did try prototyping this device, but I was never able to get anything that worked to expectations. That led me to the final design that did actually work, the sensor LED. So I think the advantages of this is that it clearly demonstrates the concept that I wanted to convey to the students. And the fabricated PCBs do add a professional look to the experiment. Some of the drawbacks were that it's a bit of a complicated design that the students aren't going to fully understand. So it kind of is a little bit of a black box that I think is a little bit of a drawback for a physics activity. And the fabricated PCB did increase the cost of the activity. So to arrive at the final product here, there were, 3 iterations that I went through. The first was breadboarding the design, just slapping stuff together and getting something that, looks like it works to demonstrate feasibility. Then I started spinning this onto PCBs. The first design was a 2 PCB design. The idea being one PCB has the sensor LED on it and all the amplifier electronics, and then we have the indicator LED on a spatially separated board that the students can hook up to each other. This required a bit more student assembly, which I thought was kind of a good thing because it would engage them more. But having the 2 PCBs and all the jumpers and connectors going into this made the design way too expensive, and the 2 PCB setup was a little bit clunky to move around and use. That led to the final version of a single PCB. This has a button cell battery on the back for power, and then little jumper cables here to just stand the indicator LED off so that it's not going to, so that when you illuminate the sensor LED, the stray light from that is not going to, interfere with seeing the LED turn on. So some of the main takeaways here is I think this was a successful demonstration of the photoelectric effect in an experiment for middle school students. And the collaboration did allow for the development of a better activity. We were able to explore more ideas and incorporate a more comprehensive lesson plan because of that. And the video development, I think, added a lot to the final activity. The main downside was the collaboration required more development time, but I think if you plan for that accordingly, you can definitely mitigate that. So thank you, and now I guess we're on to the next talk.
My name's Kimberly Becker. I teach high school physics in Lafayette, Colorado. My undergraduate degrees in physics and my master's degrees in physics education. Daniel, want to introduce yourself too?
Yeah, my name is Daniel. I'm a laboratory instructor at the University of Chicago. So my background is engineering physics, and I did my PhD in atomic physics. So my job is about developing demos and lab experiments for my students, especially to teach quantum mechanics to them.
And then, great. All right. So yeah, I wanted to talk about PhysicsQuest Quantum in the classroom. And I'm really excited since we had some of the content developers talk already about some of the lessons that I'm going to show you how they played out in a classroom setting. So we can see like the whole path of the outreach, development, collaboration, and then implementation in the classroom. So this is at a high school classroom. And so I know some of the lessons were developed for the middle school level, and then I just adapted them for my high school students. So we've got Centaurus High School is where I teach. And here is one of the lessons that was developed that I don't think we got a chance to talk about. It's the dancing matter lesson, or I missed some of the first start of it. Did we talk about the dancing matter one or not? Anyway, the dancing matter lesson is this, we've got X-ray crystallography modeling activity where you can see that little crystal structure that's in the middle there. You cover that up, the ping pong balls and the springs, you cover that up with a cloth, and then you toss ping pong balls at it. And the students try to figure out what the structure of it is without actually looking at it by looking at interference patterns. So here's some pictures of the students doing the dancing matter activity. They are having fun with that one. Then the photon frenzy, which we just heard about from Reggie, was awesome. So thank you so much for spending all of that time to develop these easy to use LED devices for the students to test the different color filters, the yellow filter and the blue filter. So I have a video, a really short video of students interacting with the filters. So I didn't videotape everything. This is just a little clip, but here it is. So, so like Reggie said, having them make the predictions first about what filters are going to light it up, like looking at the filters ahead of time. They looked at the yellow filters and the blue filters just with the flashlight behind it, and they thought, oh, well, the yellow light looks brighter. So their predictions were that the indicator light would still light up with the yellow filter. And clearly they were really surprised. It ignited their curiosity. It did exactly what it was intended to do. And then there were tons of questions that came after that, and the students got super invested in the activity. And because it was the high school level, I decided to step it up a notch, and we did like a full virtual lab using the photoelectric effect simulation through PhET. So that's why there's a little snapshot of that. And then the students carried out a full investigation and figured out what the cutoff frequencies were, and did a little math with, figuring out the maximum kinetic energy and the stopping voltage, and learned about all of those sides of the photoelectric effect. But having the photon frenzy activity to kick that off got everyone invested. So thank you, Reggie, and your team for developing that. It's like completely paid off, and it's probably the best photoelectric effect lesson I've ever done while teaching. So it was pretty awesome. Next. So as we heard from Zach and Malcolm about the game Tangle, this one was really fun to play out in the classroom. I think the hardest part was explaining the rules and getting students to understand the gameplay process. So I just took a classroom video walking around with my cell phone. So again, it's not great videography, but it at least shows students learning how to play the game. So you can see that in the classroom, kind of see the outcome of all of that work you did to try to ignite curiosity and make it more applicable and relevant. So you can hear, you can hear that they're having fun with it. They're engaged. Like everyone in the class was fully invested in this. They got a little competitive. You can hear the laughter in the background. So students were just enjoying this activity as a whole. So for some overall reflections and takeaways from the high school classroom, is that this is like all of the lessons that have been developed through the this PhysicsQuest Quantum, I guess, stream of lessons have been fantastic at engaging the students and prompting questions. I've had a lot of interesting conversations with individual students. They want to find out more. They're interested in quantum science. They're interested in possibly like pursuing quantum in their future studies at the university level. This outreach initiative has been highly successful at the classroom level. And then not only that, so like I was a part of the pilot testing them all out. But then we shared them at the American Physical Society Teachers Day in Anaheim for the Quantum Jubilee workshop. And that's how I got connected with Danyel. And that was a really valuable experience as well, because there are at least like, I don't know, like 38 teachers who probably each teach 100 to 200 students. And they all got to explore the lessons as well and try them out when we were at the workshop. And now they're taking those out to their classes. And so there's just thousands of students that are getting to experience this now. So it's pretty awesome and inspiring. And I'll turn it over to Danyel.
All right. Yeah, I just wanted to share one idea about the activity that I developed, and I think it was mentioned before through the presentation, is this concept that using quantum ideas that usually thought only when you get to undergrad, maybe senior undergrad, or even until you're in graduate school. But I think we're moving more and more towards actually trying to teach these ideas much earlier, hopefully since high school, even before. Two ideas that are very important for quantum mechanics are probabilities and correlation. And I think we can definitely do a really good job about explaining those using things like playing cards and dice. And maybe we can go to the next slide. I think that's really good. One, because these are things that are very low cost and accessible. People know them already. And it makes it more relatable so that the students have something that they can picture and play with instead of thinking about some really abstract idea. So one of the activities that I developed, we go to the next slide, is just a game where you start playing with cards and you draw correlations between the pairs and try to come up with an index that tells you how can you describe these correlations. And this is almost as a one-to-one mapping to the experiment that the people that got the Nobel Prize in 2022 did about entangled photons, and then how if the particles have classical properties, then that stable like establishes a limit in the kind of correlations that you have. But then if they are entangled, then you can go even beyond. I have tried this game with students from middle school all the way to undergrad and graduate school, and also with just adults. And I think people like it because if you present it like a game, then you almost get the suspension of disbelief for free, because then you can just say, well, this is the game, these are the kind of rules that we're gonna be playing with, what kind of pattern can you see? And then people really appreciated that. On the one hand, you're keeping it simple, but on the other hand, you're actually getting very close to the actual concept. So I think overall, it's been pretty good. And my main takeaway message is that you can actually just, if you sit down a little bit, you can come up with your own example using very simple things that actually map all of the math related to quantum mechanics very easily. So just like this example, I'm sure we can make maybe more, a little bit more. I think that's all I wanted to say.